So after density, probably the most important property of a fluid is called the viscosity. This measures how much resistance there is for the fluid to flow. So think of things like honey or water. If you pour them out of a jar, they're going to flow differently. Honey has a higher viscosity, so it flows a lot slower. So that's what viscosity measures. It's also sometimes called how thick or how sticky the fluid is. In terms of oil, it's called the weight of the oil. So a lot of times for your car, for example, you have engine oil that's something like 10W30 or 5W30 or 10W10. So those give you the relative weights of oil. So 10W30 would have 10 weight and 30 weight in there. If mu equals 0, then the fluid is called inviscid. Now in real life, there's no such thing as an inviscid fluid. There's always going to be some resistance as the fluid tries to move, as the particles kind of shift and move around each other. But in some situations, mu equals 0 is a good approximation, so we keep that around for those situations. So in general, for fluids, viscosity is a function of temperature. So as the temperature changes, viscosity changes as well. That's why in the oil example we had before for your car, 10W30 means that there are basically two different types of oil, viscosity of 10, viscosity of 30. And the reason you need that is because in the summertime, when it's really hot, viscosity of oil is going to go down. So you're going to need a heavier or thicker oil in the summertime because that viscosity is actually lower than what it usually is. And same thing for the wintertime. You need a low viscosity oil because as temperature goes down, viscosity goes up. And so look at my graph here for oil. As temperature goes up, viscosity is going to go down. Now that dependence differs with different fluids. For example, air, as the temperature goes up, the viscosity actually goes up as well. So there's definitely a temperature dependence for any fluid, and that temperature dependence changes based on the fluid. Generally, if you want to find the viscosity of a fluid, it's in the back of the textbook. There's tables and charts there for different fluids. Those are generally given at either 20 degrees Celsius or 68 degrees Fahrenheit. For water and air, the two most common fluids, there's values given for a bunch of different temperatures. So for those ones, you can actually see the dependence on temperature for viscosity for both air and water.
So this first video shows a very highly viscous fluid, so a large value of viscosity, lots of resistance to motion, so see the flow is very slow. And then the second video, we have a different fluid, much lower viscosity, much less resistance to flow, so it flows a lot faster.
A topic related to viscosity is the shear stress. And so to derive the equation for shear stress, I want to look at a flow over a horizontal plate. So I have some horizontal surface, some flow coming in. I want to know what happens as this flow interacts with my solid surface down here. Now anytime I have a fluid in contact with a solid object, I have two boundary conditions. The first boundary condition is the no penetration condition. So I'm assuming my solid object is actually solid, it's not porous. There's no way for the fluid to get through that object, so I can't have any velocity in the y direction going through my solid surface. And then the second condition is called the no-slip condition, and this is actually due to viscosity. Anytime I have a viscous fluid in contact with a solid object, it actually sticks to it. So because it sticks to it, my velocity has to match the velocity of that solid object. Here I'm assuming that my solid object is not moving, so my boundary condition, second one, no-slip condition, is that Vx has to be 0 as well at that interface. So now I want to know, what does this look like? This flow comes in. How does this solid object change that velocity profile? So obviously if my velocity on the plate has to be 0, that needs to be slowed down. Eventually, far enough away from the plate, this part of the fluid is not going to feel the influence of the plate, so whatever my flow velocity is, nice uniform speed coming in, eventually at some point way up here, that speed's not going to change, but between that point and the plate, velocity has to go to 0, so I have to have some changing velocity profile that looks something like that. Now what I want to do is look at a small piece of this fluid inside this region where the velocity is changing. So take a little square of fluid, pull it out, make it bigger, see what's going on. So on the bottom of this I have some velocity v. I don't know what it is, it's just some velocity v. On the top I have some different velocity, but I do know that it's a bigger velocity just based on the shape of this. As I go higher and higher, my velocity gets bigger. So I have some velocity on the bottom v, some velocity on the top v plus dv. Then I want to look at what happens to that at a small time later. So at t plus dt later, I have, this is going to move, so this whole chunk of fluid is moving to the right. The bottom moves at a distance of v times dt. The top moves at a distance v plus dv times dt. So there's a difference in distances traveled by this amount dv dt. So that acts to turn my square into a parallelogram. So my top surface is displaced this much more than the bottom surface. So what I can do with that is calculate the strain. So strain given by this angle phi. I'm assuming everything here is small. So if my angle is small, it's roughly the same as the tangent of the angle. Tangent of the angle, opposite over adjacent. So opposite dv dt. Adjacent, I've said this little small box has a height of dy. So angle is dv dt over dy. And then what I actually care about in terms of shear stress is the rate of strain. And so the rate of strain, just take my strain divided by the time dt. So dp dt is dv dt over dy divided by dt. Those guys cancel out. All I'm left with is dv dy. So the rate of strain is the change in velocity over change in height. So bringing this back to the discussion on shear stress in fluids is defined to be the viscosity times the strain rate. So my shear stress tau is the viscosity mu, and then my strain rate dphi dt, but I know that my strain rate is dv dy, so shear stress in fluids, viscosity times change in velocity over change in height is how that's generally calculated. The next definition is something called a Newtonian fluid. The definition of a Newtonian fluid is that the viscous stresses are at every point directly proportional to the strain rate. So turning that into a mathematical statement, I have my shear stress tau is directly proportional, so some constant times the strain rate. Now what I want to do is compare that equation to the one we just derived for shear stress. So shear stress was viscosity times strain rate. So basically what I can see from this is that I need some constant times strain rate. I have viscosity times strain rate. So for Newtonian fluid, it means my viscosity needs to be a constant. And that constant is with respect to the strain rate dv dy. We saw before that viscosity can vary with temperature, and that's fine. All this means is that with respect to this variable, strain rate, my viscosity is constant. In other words, if I plotted it, strain rate versus shear stress, I'd end up with a straight line. That straight line would have a slope of mu, the viscosity. So in terms of this class, we're going to assume that all the fluids that we encounter are Newtonian. They all follow this dependency. What could happen in real life is something called shear thickening, where the fluid gets harder to push as the strain rate increases. So as the strain rate goes up, the viscosity actually increases. So the slope of the line goes up. So you can starts off relatively linear, but then starts to deviate from that as my strain rate goes up. So what we're going to do when we're assuming fluids in this class are Newtonian, rather assuming we're staying in this small range down here where it looks linear, basically saying we don't have really high strain rates, so this does not deviate too much from the straight line, which is generally a good approximation, as long as you're not doing anything crazy. So as I mentioned previously, density is probably the most important property for fluids. Second most important property is probably viscosity. A lot of equations has both viscosity and density in them, and they show up in a certain way. In other words, I have viscosity divided by density. And so instead of having to look up the viscosity and the density, two different numbers for the same fluid, sometimes convenient to combine those into one thing, and that one thing is called the kinematic viscosity. So mu, kinematic viscosity, is mu, the regular viscosity, divided by the density. This normal viscosity is sometimes called the dynamic viscosity, I don't call it that usually because dynamic, kinematic kind of sound the same to me. So anytime I'm dealing with the viscosity that we saw before, the regular viscosity, the normal viscosity, I just call viscosity. Anytime I want the actual kinematic viscosity, I will definitely say kinematic viscosity. So if it just says viscosity, I'm talking about that guy. It says kinematic viscosity, I'm talking about this guy. Last thing associated with viscosity is the surface tension. So you may have heard of this or seen this before. If you take some pepper at home, fill up a glass of water, pour the pepper flakes into the water glass, some of them will float on top, some of them stick down. The reason for this is surface tension. It really depends on how those flakes of pepper hit the surface of the water. So if they hit the surface of the water relatively flat, they're going to float. If they hit the surface of the water vertically, they'll actually sink down to the bottom. And this is again basically due to surface tension. What this does basically means that fluids do not like going around sharp corners. So in this situation, my fluid does not want to go around these corners, so it's trying to hold this thing up there because it'd rather do that than go around the corner. This guy goes down deep enough that it's only a small corner to go around, so this fluid doesn't mind doing that. It'll do that, and the thing will fall down to the bottom. You can also do this with razor blades, so really heavy things, you actually get to sit on top of water. As long as you place it relatively horizontally, it'll work. The last concept for today is called vapor pressure. To introduce this, simple question: what temperature does water boil? Of course, answer to that, 100 degrees Celsius or 212 degrees Fahrenheit. But now the question is that always true? So these values of 100 degrees Celsius or 212 degrees Fahrenheit are only for standard atmospheric pressure. If the pressure goes up or down, these values will change as well. If the pressure is higher, these numbers will be higher. If the pressure is lower, somewhere like at high elevation like Colorado, water boils at something like 97 or 98 degrees Celsius. So the boiling point goes down as well if you have lower pressure. Now if you get to really low pressures, you can actually get something called cavitation. So at really low pressures, water is going to boil at down to maybe 20 degrees Celsius. So even if you have water at 20 degrees Celsius, you have a really high velocity in there, you can end up with some bubbles forming, and that is kind of the water boiling, but at a really low temperature. And so this is the concept of vapor pressure. You may have seen a picture of a propeller, a boat propeller in water, taken as it's spinning around. You'll see bubbles forming on the outside edges of the propeller. The outside edges is where the velocity is the fastest, and we'll see later in a few lessons that velocity and pressure are inversely related. So the higher velocity means the lower pressure. So on the outside of those blades, where the velocity is the biggest, is also where there's the lowest pressure, and that's where you see bubbles actually forming, and that's what's going on. The water is actually at such a low pressure that it actually boils and turns into a gas. So a couple examples. First example, have a 1/10 of an inch layer of glycerin flowing across a flat plate at 15 inches per second. Want to know what the shear stress is acting on that flat plate. So solution to this: to find the shear stress, I need the viscosity and dV dy, strain rate. So glycerin, table B2 in the book, I can find the viscosity value for glycerin of 3.13 times 10 to the negative 2 pounds second per foot squared. So that's my value of viscosity. And then to find the strain rate, dV dy, I'm basically going to look at the change in velocity over a change in height. So as this thing, as this fluid in contact with the plate, no slip condition. So when it's in contact with the plate, I need to have 0 fluid velocity. That's at y equals 0 on the surface of the plate. Then at the top of the layer, I know that my fluid is going 15 inches per second, and my height at that point is 1/10 of an inch, 0.1 inches. So I can use that to find the change in velocity over change in height. So shear stress, tau, viscosity, 3.13 times 10 to the negative 2 pounds second per feet squared. And then change in velocity, 15 inches per second minus 0. Change in height, 0.1 inches minus 0. Gives me total shear stress of 4.7 pounds per square foot. Now usually shear stress is given in PSI, not pounds per square foot. So divide this number by 144 square inches per square foot. gives you 0.033 psi as the shear stress on the plate. This is technically the shear stress in the fluid, but kind of like Newton's third law, equal and opposite forces, I kind of have equal and opposite shear stresses here. So shear stress in the fluid is equal to the shear stress on the plate at that point. So second example, I have a fluid with a kinematic viscosity of 3.2 times 10 to the negative third meters squared per second and a specific weight of 57 newtons per cubic meter. I want to know what its viscosity is. So again, here viscosity is just the normal or dynamic viscosity is mu. That's what I'm looking for. So we know that kinematic viscosity, mu, is regular viscosity, mu over rho. And then we also know specific weight is density times gravity. So combining these two, rearranging this guy, mu is density times kinematic viscosity, but then density from this guy over here is gamma divided by g. So replace density with gamma divided by g. So I can find my viscosity by taking specific weight times kinematic viscosity divided by gravity. So doing that, viscosity is 57 newtons per cubic meter times 3.2 times 10 to the negative third meters squared per second divided by 9.81 meters per second squared gives me a value for my viscosity of 0.019 newton second per meter squared.